All right, so this is Thanksgiving week, so I really appreciate that many of you shows up. I'll also be here on Wednesday, and also I'll bring some chocolate because because that's something there is a good side of it, there is a bad side of it. Good side of it is obviously you'll all have chocolates. Bad side is it's not good for health, right? But I have usually on Wednesday we don't have class when we have no Zoom because we have a Zoom meeting anyway. So it doesn't really affect if somebody is traveling. They can always attend the lecture remotely wherever they are, or they can also look at the slides after the class. Because I'm here, it's more effort for me to teach from home than coming here. So that's why I'm going to come here anyway. So if you can't show up, it's fine. I understand you have to go to see your family. Okay, so lecture 17, that's this. We have 2 more weeks, including today or this week. I just want to mention that where we are in our syllabus. So if you think of final, that's the only thing remaining except the homework. One more homework. There is no 7 homework, okay, because I merged together homework, so this is going to be total 6 homework, okay. And these are the 5 different things that will be on the finals, except the last week. Last week, week 10, whatever we cover, I don't really put questions on them in the finals because I know that it's the final week. So everything before air quality or including air quality will be part of the finals, okay. The last lecture is basically applying everything we learned to sustainability concept, resource recovery, energy, all that. So those are basically concept, and you learn how to use those, apply those in different field. So this is something take home message from this class. So you are going to concern about week 6, 7, 8, 9. Anything covered within those are going to be part of your final, okay. So that's starting from drinking water treatments, then you have wastewater treatments, then solid waste management, and air quality. So these are the 4 things that you will be working on for your finals. This is not cumulative, but as you see some of the homeworks, the concept that you learn in the midterms are coming back. For instance, you got to know what is BOD, okay. Also, you got to use mass balance concept, even though you're not deriving them, to solve different problems. One thing I forgot to mention here, that quiz, we still have one more quiz. Quiz 3 is on Wednesday. And this is again going to be due until Thursday midnight. So it will release on Wednesday morning or Wednesday during class. And you can take 15 any times before Thursday. So this Wednesday. So just check whether this is this class. Yeah, week 9. So every 3 weeks there is a quiz. Okay. So this is quiz 9. The quiz 3 on week. Is this not this Wednesday? Just check on syllabus. I don't really. Is that next Wednesday? Just check syllabus wherever it is. That's the time it will be. I am sorry if it is on syllabus, whatever it is going to be in the same time. I'm not changing the time. Okay. Check on the syllabus. So check syllabus. You know what? Why not we check right now? Because this is an important thing. Okay, so if you see syllabus, where is the syllabus? Okay. Okay, so if you see syllabus, oh, you're right. So quiz 3 is not this week. Okay, so next week. I'm sorry. That makes sense because you want the quiz to prepare you for the finals. What concept you should know. So okay, so the quiz 3 is the final week. Okay, or the not final week, the 10th week 10. So that's why it is not in the slide. So I was thinking I'm forgetting. Okay. This is next week. That's December 1 to 2 or something. Just check what's the dates. Okay, so I know I got some emails from you guys for PT. So instead of responding to all of you, I put at least 16 PT for that class here. So if you're one of those students who are not CE students, you can't enroll the next class that I teach, that CE164, which is a sustainable waste management. You need PT numbers to enroll it. Right now there are 44 students. The class size is I think 60. So that goes quickly. So make sure that you use this PT because I put it public. That means, whoever go to the first one, that will be gone, so that means keep trying all the 16 until you maybe the first few already some students have and used it. If none of them works, then send me email. I'll put another 16 here. Okay, but the reason I put 16 is because there are 44 students enrolled, so there are only 16 around remaining in their class. This is open for only winter. Yes, the class is in spring quarter. I teach another class called CEE153, which is a green infrastructure. There you design basically stormwater treatment system building in a way that could help clean stormwater and also save energy. So those are that's a very different thing. This is more on waste. In fact, what we cover in the last class is basically 50% of that class in a condensed way. More details about those. Okay, so I'm just going to give this one so that it doesn't stop. Okay, let's see if I squint. Okay. Okay, so today we are going to learn a couple of things. Air quality is obviously one of the criteria. We are also going to learn just seeing how I can minimize this. Yeah, the screens for some reason this keeps showing up. I don't want that to be on the screen. Okay, well, as long as it's not interfering on the screen, it's fine. Okay, so there are two aspects of it. First, we are going to learn about how the municipal waste has been managed. Okay, that's something continuation from the last class, also part of the CE164. And most of the things, why it is important, because landfill is the one of the main treatment technology for many of the waste we produced. And landfills are called, before they are designed to just receive the waste, nothing else. It's a waste receiving facilities. But now it's more on resource recovery facility, means like wastewater treatment plants, they are also designed to harvest energy. Okay, so and municipal waste is the one that actually produce energy. So we are going to talk very briefly about how it is done. Then we go to air quality, because landfills are also the biggest one of the largest emission of methane gas before, because you dump all these organic waste, they produce methane, they will go to the atmosphere. And so that's what they are doing actually. They are capturing that methane and creating energy. But then we are going to talk about air pollutions. So like we have been talking about water pollution for almost like 8 weeks of the class. Now we get into air pollution. The concepts are exactly similar. There is nothing different. The only difference is, in water you have soil or other things that can stick with, the pollutant can stick with. Air doesn't have any boundary, just moving. So the only thing that matters is distortion. And so it's much more simpler than water pollutions. So we are going to discuss about that mass balance concept for air. So again, all you have to know is how the equation is written and what's the solution, which is much simpler than water, and then how to use it to predict pollutant concentrations either indoor or outdoor air. So those are things we are going to learn today and next class. That conclude mostly anything you want to know about environmental engineering. And the next class is about next week. We are going to apply all those things to sustainability or energy harvest or all these newer problems that we are dealing with. So that's more of a brainstorming of why we need to learn all these things. Why is it useful? Okay. In homework 5, I know that there are some questions related to mass balance. So I just put it here. Every mass balance, you may need it for the wastewater treatment problems. And these are useful for your exam questions as well as your homework questions. And I didn't get the chance to respond to the questions on campus where one of the students asked this question, which is very interesting and also very reasonable in terms of logic. The question was, when you think of mass balance of a suspended solid in secondary treatment plants, let's say this is the one we are trying to see, what is the mass balance? As you see, there are pollutants, let's say X coming in. So X coming in, and then you have Q, let's say whatever that Q is, that's QS plus Q. So this is QS. Based on whatever here, it has to be same here because you don't really lose any water. And then you are here, you are basically doing QW, that's the flow, minus Q plus QR, because all of them are leaving the systems. And then your concentration is XW. And then some of them recycling, some of them are recycled, which is QR. That's the fraction of the flow that you are dumping back into the aeration chamber. And waste activated sludge, that's the one you are going to remove it. So I'm talking about the mass balance of this particular reactor. So you have one in, one out, or two out. If you don't want to write about what is out, you can say how much is removed, okay? Because whatever removed and the settling, that's the thing that removed or out. So a lot of times, instead of writing this what is out, which is written here, that's QS times X is what is coming in, and everything in the right side is the tube flow that leaving the system. That's very easy to understand because you have one in and two out. But a lot of times, this is the one factor you don't know, you are not given the flow rate, but how much fraction is recycled, how much fraction is wasted, or the QW. So because you don't know those two terms, a lot of times you can't use these equations. What alternately you have is how much particles are settled. All the particles that settle are removed by that second flow, that waste and recycle. So this equation is replaced by this term, which is basically area of clarifier. This is settling velocity. And this is the concentrations. Or clarifier. Your reactor is a clarifier. And everything looks okay. If you see the derivation, how you get that term, check the homework 5 handouts that during the office hour I derive it, how you get this term, so that you can see. The question is what concentration you are going to use. The students that raise question is this what you are going to use, the influent concentration, because that's the one kind of settled, or is this one who are going to use the effluent concentrations? So his or her argument is that you get the dense particles, like all the particles coming in, and they are the one who is experiencing the settling. So why not use that one, influent? Why to use the effluent? So think of this way, even when you start the experiment, imagine there is nothing there. Clarifier has water. When you, let's say wastewater is started just now, you just dump the very first wastewater that comes from the secondary the aeration tank. You just dump some volume of it. what will happen? This is a clarifier, it's going to disperse, right? Everything will go into diluted. So that dilution factor is not accounted for if you're going to start using the influent. So all the time you have to assume whatever coming out is the one which is being reacted. That's just the way of making simplified way of accounting for dilution, all the other factors. So anytime you're looking for reactions, always use the effluent, because that's the assumption. Everything that inside the system is what's outside the system. Another way to say is everything settled is not reacting anymore. That's reacted. So you are only accounting for that suspended in the system. And the things that suspended is basically what is the diluted factor. So that's why always use the effluent. This is a use concentration in effluent, not, even though intuitively it makes sense to think that the what is in the effluent is being reacted or being settled. That's the same reason if you see all the reactors design you use, you always use the effluent one, not the influent one. So that's the same argument. The reaction should be happening with what is being getting into the system. And then there are other, this is the mass balance for entire treatment system. Entire treatment means primary and secondary. Yeah, if that's the case, yes. So I put all these mass balance. So not sure which one you need for which questions, but at least you know these are all that you need to use ever in the exam questions. And every possible exam questions are given in the homework. And there are extra example questions. TA is going to share the question so that you have some practice on those homework, so that you know. If you don't have that, I'm going to share that questions on email or put on CCLE so that you see those. Okay, so that's all about the homework that you have. This is due on Wednesday, this Wednesday. I'm going to release the next homework, which is on air quality as well as the solid waste management. So that will be released on this Wednesday, and you have everything you know to solve those questions on the next questions. And this will be due on Wednesday. I will immediately release the solution on Wednesday next week. So again, I'm going to warn you that do not ask for extension after next Wednesday, because we have basically that's the last class. I have to release the solutions. Okay. And I'm grading the midterms. It's taking a while. I underestimate the amount of time it takes. I have help, obviously, but still, I want to make sure that it's all graded fairly. And again, for all homework questions, you have until the basically end of the final weeks to ask for regrade request for any questions that you have, including midterms, everything. You can ask for regrade request for everything until the final day of the final week, because I'm not going to release the grade until after that week. So that means you, before that, anything I receive, I'll consider those to see if actually there is any issues. Okay. All right, so municipal waste management. Last class, what we learned is about how to manage hazardous waste. But most of the waste in what we use at home is not hazardous. And those are by far the largest volume of waste produced in big cities. So how are you going to deal with those waste? And those waste also cause pollutions. For instance, think of what happens in your everything that you collect in your trash can. At your home, anytime you just monitor how much stuffs you are putting on your trash can, you'll see that many of them are plastics, because that's the wrapper or the stuffs that you dump inside. Some of them might be recycled materials, but you still put it inside because there is no other way. Then many of them are also organic. For instance, wasted food by far one of the reasons. So we buy too much stuff, put in the refrigerator, the things expire, then we dump it here. Sometimes we cook too much and we can't eat it. So these are the stuff that goes into municipal waste. And where they go, if it is not food waste, the mixed waste, they goes to landfill. There's no other things they do with it. So So that's why it's very important to understand how the landfills are designed. Landfill design has evolved over times, and we got to know how they are evolved. Before, it was more about collecting all the waste. Landfill sounds like what is landfill means. Dig a big hole, fill with all the waste, and cover it with soil. So you never see those. So it's like burying the waste and not worrying about it. And so the reason why that technology doesn't work if you keep doing that one is where two risks. Number one, what if there is you bury all of them, but they are going to decompose with time. When they decompose, they produce gas and they produce liquid. Okay, imagine if you have solid waste. Do an experiment like this. You have salad, put those in a container, leave it outside. After a few days, you'll see those salads are all like decomposed. Only thing you see there is liquid, if not fungus grown. And that liquid, if it's not evaporating, that's basically those liquid you will see. That's a slurry of liquid. It stink because it has stopped, right? So that's exactly what happened in the in the landfill. But it also, because you can't really make them very closed, you're not producing methane there in your home because kind of the lids are not so tight. If it's completely tight, no air coming in, you'll produce methane. Okay, and so those methane gas is going to go atmosphere. That's causing greenhouse gas emissions. The liquid is going to groundwater, is going to pollute it. So the whole goal of this landfill is to make the waste stay there. Any byproducts stay there. But liquid, like liquid and gas, they can move, right? Because that's the gravity will make the liquid move, gas will move up, right? So you can't really contain them unless your boundary is very small. And the solid, when they convert to liquid and gas, the volume also expands. So imagine you dump all the solid, produce methane, unless even you contain them, those gas will expand. So it's going to leak or it's going to explode. One of the things will happen unless you have the pressure to contain it. So the good landfill design is actually not making sure they stay inside. They also release that pressure by collecting those liquid and gas. So the newer technology, they collect those gas, spurs out everything else except methane, use that as energy. And the bottom one, all the liquid, they also collect them because those liquid has also stuff they can use. Okay, the nutrients, they have metals, they have rare earth elements, metals, which they can extract for resource. In fact, many of your cell phone, other electronics has gold. They use gold coated material. So imagine you dump all of them. So it is basically a gold mine. And the point is it's expensive. So the cost of extracting those gold will be more than the gold price, but still it's a gold. So that's why you're going to learn about how to design them differently now. So that's why now if you see today's landfills are designed in a way that's called resource conservation or recovery. That means the biggest part of landfill design is recovering that waste or valuable materials. So this is just a few things that you have to remember. The landfills are regulated under RCRA subtitle D, solid waste, and C. D for solid waste, municipal waste, C for hazardous waste. These are typical interview questions or PE questions or FE questions, fundamental of engineering. These are things you have to regulatory standpoint, you have to remember. Anytime you hear D before waste, that's a municipal waste. Anytime you hear C, that's basically hazardous waste. All the landfills we are going to cover right now is nothing to C. We are not designing landfill for toxic material. They are designed different way. I'll tell you what extra, but mostly what we are going to cover is for D. That's municipal waste. They're not hazardous. So that's why I say there are at least the three types broadly. Municipal solid waste landfill. That's basically what we are going to cover. Industrial waste landfill, where you have specific type of toxic materials or stuff. Sometimes it doesn't have to be toxic. For instance, construction. Every time a building is demolished, it has concrete, it has woods, it has steel, it has so many things. They try to scrap those, separate the waste type so that, for instance, all the steels, they recycle it if they can. But most of them, if they don't, they just put it there. Okay. So that's just the one example. And for instance, another thermal power plant, if you have a lot of power plants and it produce basically coal is the one is burned, you produce ash, and those ash will be dumped into that big mines. So those are the different type of design. This is not same as municipal waste. And then of course you have hazardous waste landfill. This is nothing to do with the solid waste. It can contain all kind of toxic materials. The difference is how do you protect at the bottom, because hazardous waste you have to have multiple safety regulations. So that means the bottom layer has to be so foolproof that it's not going to leak ever. And you can't put those kind of waste landfill in a very near to the location where people lives, because what if there is an earthquake, things open up. So those are the external factors, but designs are just the more cautious design. So these are the very different things you have to 5 different things you have to remember when it comes to. Now we are going to cover about everything about municipal waste. First thing is what type of waste. It's kind of a quiz question. What type of waste is received by municipal waste? Type D, you know that it can be hazardous. That's why they keep saying do not put any battery or anything into your trash can, because those are hazardous. You don't mix hazardous with non-hazardous. So all these municipal waste are non-hazardous. That's the key. Location restrictions. So where you are going to put this landfill? First of all, you have to protect the environment. So that's why removing those waste away. You don't want this landfill to be very near to a place where things can spread, which is basically wetland, rivers. Near the rivers, you don't want to put landfill. Near the wetlands, near any place where there is an earthquake probability is high, because you don't want things to be coming up again. And then also any floodplains. The reason is you don't want the landfill to be covered with flood water. If it's covered with flood water, it will compromise that cover, because a lot of landfill will not have a cover when it's operational. They're just dumping stuff. They don't have time to fill up. We'll just get to that. So you don't want to in the cover place. So every point is kind of a quiz question. So you know what are the restrictions. These are just a conceptual point of view. Then this will account for locations. What kind of liner you need to have? Liner, the whole goal of liner is to protect the permeate, or to have the exchange of liquid, or you prevent the exchange of liquid. For instance, at the bottom you see there are different liner here. The idea here, you want the liquid to stay inside it. You don't want them to get into groundwater. So those liners has to be there. And what kind of liners? Or this membrane at the bottom varies between different type of landfill. For industrial landfill, it's very different from hazardous waste landfill, which is very different from municipal waste. Basically, the protections. Yes.
For the bottom, is that like naturally, or people feel it for the
Bottom
bottom?
means this area.
Like the thing holds like all the like not going to the top.
Oh, so those are built.
They are built.
Yes. So basically, start with a pit. There's nothing there. Then you create this layer. So we'll get to that. So we'll see. And for landfill, always assume the worst is going to happen. That means you have to prepare for that. So the worst thing that can happen is basically leachate leaking. Okay. And so because of that, you have to actually collect the leachate, because the liquid will rise. And if you have too much liquid, that also prevent degradations or decomposition of the waste that you just put in. You want the decomposition to happen. That way it's kind of the waste become non-waste. It becomes soil, right? That's what you want. But that's the reason you have to collect the leachate. So there are pipes underneath to collect the leachate. And you see these big tubes, those are for collection of methane gas. Okay, we'll get to that. It's just a well that collect methane gas, or just collect the leachate, so that you know. But that's not how it actually look in the real world. I'll get to that. Then the next thing you have to remember is how do you operate it? Because it's not like you have a big landfill, that big pit, and you dump everything and just keep filling up. That's not going to work, because every time you wet, there is a rainfall that will come and fill with the water. You don't want that to happen. In Los Angeles, it's not a factor because it doesn't rain that much. But imagine landfill in New York. It rains frequently, so you don't want the rainwater to get in. So every time you have a soil waste layer, you have to find a way to prevent the rainwater to get in. So they, for Delhi, what they do is they protect all the waste, they dump all the waste, and there is always a line, layer by layer, they treat. So we'll get to that. So that's the operation practice. How you cover them, how frequently you cover them, and what kind of inch of soil you cover, because that cover is to protect the rainwater to get in. Then also, because you have a landfill, you are mandated by monitoring groundwater. Even though you did everything possible you can, still accident can happen. How do you know that groundwater is not polluted? So you have to monitor the groundwater downstream all the time, just to ensure that your landfill is not cause of the pollutions. Then once the landfill is completely reaches lifetime waste receiving material, so that means the entire space is filled, it can no longer can receive all these other waste, you have to close it. You have to close it and protect it such a way that it's not going to cause any hazardous other stuffs in future. And typical lifetime of a landfill is around 50 years, 30 to 50 years, so it's pretty long time. But then you have to come to the end at some point. So now this is kind of a let's all the see the numbers, everything is written. So let's think of conceptually. Let's start from the bottom. That's more easier to understand. So number 14. Number 14 is the first layer that, imagine you dig a hole. Okay, so what you're going to do is you're going to put some kind of, because you basically native soil, so you find a location which is not near the wetland, near the rivers, near the stuffs. Once you find the location, you basically create as big hole as possible so that you can start filling those materials. The very bottom, before you put the membrane, that number 13, you have to grade it evenly. So that's why you have to put this number 14, prepared subgrade. So basically it's a, it could be clay, but it's something that make it evenly flat. Okay, so that's basically subgrade soil, native soil. You just mix it well enough to put it. Then number 13. Number 13 is the part that prevent any leaking to happen. That could be anything, but mostly it's clay, because you know that clay materials will have very low hydraulic conductivity. So even you have a water that on the top takes 500-600 years to get into that bottom. If you use Darcy's law, use the hydraulic conductivity Q equal to KIA, use that formula, you realize the velocity of water through this one is so slow, takes more than 500 years for water to come from there to here, unless there is a crack. Okay. And landfills are designed, at least to operational point of view, is 50-60 years. Then it should be protected for another 1,000 years. Now let's put this way, for municipal waste, 500 years, most of the waste will be all soil. 500 years is enough for many organics to decompose to nothing, or carbon dioxide or methane. So that's why it's kind of sufficient. So most of the landfills, in municipal landfill, you put this clay. Okay, you don't put anything else. You put plastic membrane, all that, that's fine, but just most material is clay. So as you see, it's called compacted clay. That's the reason. If you use Darcy's law, you'll know that it takes 500 years or more. In fact, there is an example question on that. The next one, your goal is to, so you have again another number 12. If you see number 12, that's basically geomembrane. Where is that gone? After the clay, you put some kind of plastics or materials so that kind of protect the clay. And you don't want things to leak into the clay, because once it goes there, and obviously it takes time. It's a matter of time, it will go to 500. Why to go there at the first place? And then on top of that, you want something to collect leachate, because all the liquid decompose, they will slowly percolate down and you will have all the liquid system. Here, your goal is to collect water as quickly as possible. You want to remove the leachate away from the system so that you can treat them using your water treatment plants or whatever things, but you have to remove them as quickly as possible. So now your goal here that your hydraulic conductivity has to be very high, because you don't want this leachate to lie around there. You want them to be drained very quickly possible. That's why you see this picture, they are gravel. Okay. Let's go to this one, leachate collection system. There's perforated pipes surrounded by bed of gravel. Gravel has highest hydraulic conductivity because you basically have a lot of gaps so that things will just get out. So again, your goal is to do that. And then think of what is there on the number 10. Number 10, you have to have a membrane that allow the leachate to come in, but not the waste. Okay, so you don't want the fine particles or the waste material, the decomposed waste to come inside that layer, because they will clog the entire gravel. You want some kind of filter that will only allow the liquids to get in, not the solid. So that's why you see number 10 is a filtered geotextile. Basically, the whole idea of this one is to allow the leachate to get in, not the solid particles. Okay, that's why you see this fall. Then after that, number 9, what is that? Number 9. So the difference between, what is that? Number 9 and number 11 is that you see the gravel layer is very big, right? So it's a big gravel, so the gap is high, so things will fall very easily. Anything. So you want some kind of protective layer which is larger enough particles so that things will slowly percolate through it, but it's also not going to fall into the gravel layer. So that's why you have this 9, which is kind of a similar thing as gravel, but it's mostly the size of the particle is smaller. So it could be sand, it could be pea gravel or very small particles. That way, it kind of protect. Where is that gone? This number 9. Basically, imagine this is sand. So it's allow the water to move in, but very fine particle will be filtered out, so that it will never get to that membrane. Above that, your waste. Okay, so number 8 is basically your waste. You are dumping. That's the first set of waste that's dumped into the landfill. After it become like 1 or 2 feet, whatever their requirements, whatever that, basically the truck will come and dump, create a layer, and then truck will drive on the same waste and dump it next layer. So it goes like this, it's like, imagine this is going to fill. So truck will dump here, go to the next here, then it's driving on top of it, so it's compacting naturally. It's go there and it's filled completely. Once it's completely filled, you have to protect that layer. So that's why you put the number 7, which is basically you are covering them so that no rainwater can get in. Okay, so that is completely covered, so that's protected from now on. So that number 7 is daily cover. Every time you dump something, you cover it. So truck come in, after dumping everything, they will cover with the soil or layer of stuffs, so that the road is built. So that layer you're not exposed to atmosphere. So the wind cannot blow those waste, because imagine plastic and you dump all those and the wind will blow it. So every day, at the end of the day, they cover that. So basically that size is 6 to 12 inch of soil or other approved materials. Because naturally people use soil because that's what they dig out there, so it's available, so they don't have to haul it all either. And then you basically keep repeating as many layers possible based on the depth. And once it's kind of ready, like imagine it's all covered and the landfill is the end of their life cycle, or the end of their, you can't go any higher. Then you start covering them the same way that you start in the bottom. So you start putting the number 6, which is basically clay. The goal of this one layer is basically not to have any rainwater getting in. So because you don't want the leachate to be mixed with rainwater. You don't want to treat rainwater, because what's the point of the clean, right? So number 6 is basically same thing, same materials in the reverse way. So clay, you have a geomembrane on the top of that, so that clay is protected. On top of that, you have if you see number 5, that's basically to grade it. Number 5 is geomembrane. Number 4 is a drainage layer. Number 4 over here, as you see, there's a perforated pipe. you want to create a drainage layer because rainwater will come in there. So if you don't remove them, they'll build up. The hydraulic head will rise, eventually it will rot the whole thing. So you don't want the rainwater to stay there. So you want to collect that. That's number 4. Then number 3, protective cover layer. So the membrane is not damaged, the plastic, all the things that you put. And then on top of that, you put soil so that you can have plant grow. That way it doesn't, look bad. So this is number 2 is topsoil. Then you see the plants, grass, or all the things. So that's basically how you design landfill. Okay, typical landfill, the concept behind it. So for the quiz, what you should remember is what's the function of each layer, and it's very conceptual. So you'll be able to say what's the function of. Let's say I ask what is the function of number. What's the difference between 13 and 6? Both are clear here, but what's the difference in their function? 13 here, 6 here. So their goal is to obviously prevent water, but 2 different kind of water, right? Number 13, the difference is thus prevent leachate to get into groundwater. While number 6, the very top, prevent rainwater to get into landfill. Okay, so there are the 2 different things. So just read those because you just heard about this whole thing. It's written here, everything I said. So this is why we put the example quiz. So the layer that follows, this is not a quiz question because I have not asked all the questions. There are like 4 questions here. To limit waste exposure to environment, which of the layers that prevent waste to expose into environment? Environment means above. Okay. If you are saying above environment, obviously if you assume environment could be also groundwater, you have to write everything. Okay. So basically start with this. These are your waste. What prevent those waste to be exposed to environment, which is top or bottom? So this one, and above. So the membrane, basically this membrane, this. So basically I'm gonna write here 6, 5, 6. 5 is basically waste collection, so it's really not preventing exposure. And then at the bottom is 12, 13. To limit leachate leaking. So what prevents the leachate to leak? Leachate has to be bottom. So think of all those. Number 13s and 12. Okay. To capture gas. Gas is above because gas will rise above. So to capture gas, which layer? What is not written here is that you have pipe here that collect gas from each layers, because gas also takes long time to pass through clay. So you have to collect gas before that. It's around number 7, before number 7. So those are the layers. So number 8 and all that. Seven and 8 together. In between there will be a pipe. To degrade pollutants if applicable. Obviously all the pollutants will be degraded where the waste are. So that's number 8. So one of the things that how do you know that how long the design lifetime of a landfill is based on how quickly things degrade. The degradations, the equation is basically all the time. That's the same thing as reactor design, batch reactor. So it's a batch reactor. Things are degrading at first order. So concentration equal to initial concentration times e to the minus kT. K is the degradations. You know this concept, so there is nothing new. You can solve it anytime you want. But the only thing I want to mention, which is critical for landfill design, is a lot of times the K value is given 1/time scale, right? You don't really know anything beyond it, but for landfill, it's very important to know how you get that. The K value is basically a constant times exponential E0 by RT. E0 is energy, okay, energy required to degrade for reaction to happen. The key is the temperature here. So as you see, these reactions depends on temperature. If you have higher temperatures, obviously degradation happens faster. So that means a lot of times in the landfill, because the ground, so it's kind of a geothermal equilibrium. That means the temperature will be very similar to what's the ground temperature. And in winter time, ground freeze, so the temperature will be lower, or it doesn't really rise up that much to have the reaction to be efficient. So how do you heat the entire ground? Because your goal is to degrade as quickly as possible. So a lot of times you can do that if you rely on the temperature of ground. Soil temperature doesn't fluctuate that much at the very below dip. Even in the winter, it freezes only very top 1 to 2 feet. Way below, it doesn't freeze that much, which is the landfill is. So to change the temperature, a lot of times you have to spray warm water. So that's why you have to have some kind of pipe system. You see this layer over here? There will be pipe to collect gas. The same pipe can deliver also warm water and spray on it time to time to create the temperature, because degradation happens inside this waste, not outside, right? So this K degradation right here. So the temperature, it depends on temperature. So you can spray water here, warm water. And the same pipe, when it's not delivering water, you can just use it to vacuum pump to collect methane gas. So that's the whole idea of design factor. Design factor, deliver system for warm water. What? There's a T. T is for temperature. R is a gas constant, so that's nothing new. Yes, yes. This is gas constant. This is the typical energy required, that's related to free energy required for decomposition of anything. And A is obviously a constant that depends on waste type and all that, so that's experimentally determined. E0 is just given. So that's why I say, now how do you determine the leachate production? So if a quiz question I ask, when you expect the leachate to be higher volume, is it summer or winter? So leachate is a proportional to when the decomposition is higher, right? So which conditions the decomposition will be really at high rate? Is summer, because the temperature is higher. So that's basically the similar quiz questions. Oh, okay, this is a quiz question. Biogas production in landfill is greater in which season? Summer, because of the temperature factor, right? There are reactions that actually endothermic. That means, take colder temperature will actually help it, but there are very few of them. In landfill, it's basically warm. That's why every time a decomposition happens, imagine when the very easy way to think of it, when you breathe out, like you feel heat and that's because of exothermic, produce temperatures. Okay. All right, so this is again, I keep talking that now why you use this clay layer is because of Darcy's law. Okay, so think of Darcy's law. Based on Darcy's law, you can calculate how long it will take for the leachate to travel across that 1 feet of clay layer. So that distance, depth divided by velocity of water. Velocity of water is Darcy's velocity divided by porosity. So this is porosity. So this is Darcy's velocity. And Darcy's velocity is basically Ki. So I is dH over dL. Hydraulic gradients. So if you see bentonite clay, this is the velocity. If you plug this value, that see this is a 10 to the minus 11 meter per second. If you even make it per year, 1 year equal to how many seconds? 365 days. So 1 year equal to 365 days times 24 hours times 1 hour is 60 minutes times 60 seconds. So if you put that number, irrespective of what number it is, you have 100, 1, 2, 3, 4, 5, 6, 7. So nearly 10 to the 7 to 10 to the 8, right? In that order, if you think of. Oh, somebody has a number. Fantastic. 3, 1. Oh, it's missed. I missed it. Okay, whatever that number is, you get that. So if you divide that by 10 to the minus 11 or multiply that, it's just that many meters it will travel per year. So that is still in the order of, or another way to say is, it takes almost 1,000 years to get into 1 meter. Okay, 1,000 years or more, because it takes 0.0001 years to get into something, like meter per second or meter per year. So if you put that all number, you really calculate, the value would be roughly in the order of 1,000 years. So this is why I give the questions. If a clay liner has a depth of 1 feet, which is compacted to a lower porosity, so the porosity is n equal to 0.5, how many years would it take for leachate to migrate across clay layer? Assume the clay liner is saturated with ponding of 1 feet above it. So basically, this is clay liner, and there is a 1 feet layer of water here. Okay, and if you why this region is given, it's basically the I equal to amount of head dH over dl. Height of water above it is 1 feet. The length of the layer is 1 feet. So this is basically 1. I equal to 1. So I equal to 1. Then K equal to 10 to the power minus 10 feet per second. So you're basically calculating the time. Time is distance over, if I put this one, distance n by Ki. So 1 feet times porosity is 0.5. K is and then if you write here, changed year to second. So based on what they did, so 3153600 second. What's the number? No, there will be different because the bottom is 10 or minus 10.
Yeah, that's a 1.57.
Oh, I'm sorry. This is the this will be in year. Whatever the number, 1?
158.
This, okay, so it's more than design lifetime of the so that means it takes more than 150 years to even have that liquid to get into that ground. Imagine there is also a geomembrane. Okay, so that means it takes long time if you have any leak happens, so by the time you hope that everything is so decomposed there is nothing left. Okay, So the last thing I just want to say that how they do this resource recovery. So basically what they do is they collect the methane gas, like you see those pipes, they collect methane gas and purge it. There is a gas scrubber because it's not just the methane that's produced. There is hydrogen sulfide, mostly carbon dioxide, methane, and other gases, which is a very small component of it. So the gas scrubber that you see over here, that basically remove every gas except methane. Okay. And then those methane gas, you have to compress it because you can't store them in a for use. And then those compressed gas is delivered to a generator, which is basically a power engine, which you burn the methane gas to change to carbon dioxide, and then you produce is basically move a turbine, and then you produce electricity. Okay, so many of the landfill design are actually producing more energy than ever need, and some of the same energy can also deliver to ground to heat up the ground so that you can have higher efficiency. So again, methane production is an anaerobic system. So that means, you got to have low oxygen limit. So this is what I was talking about, gas collections. So every layer you have to have gas collections. By each layer you are collecting some gas and using the same thing to deliver, to either collect leachate or deliver gas. Okay. And again, these are things you can see, read it, so that you know the details, but I'm not expecting for quiz, just know how it works. Aerobic bioreactor, one of the things you have to know, anaerobic process is slow, aerobic process is fast. So if you are creating an anaerobic process, it takes long time for those waste to decompose. Aerobic is much faster. So if your goal is to make sure that this landfill, all the waste, like let's say food waste, are completely decomposed within few years, so that the things settle, and then you keep pouring, because things will settle. Once the food waste is decomposed, the layer will shrink. So that means you are receiving waste for a long time. Okay, so that's the reason this is preferred, because the real money is basically collecting waste. Every time a landfill receive waste, they pay people pay for them, right? So that's the main money. Energy is very little aspect of it. So that's where the aerobic design. Aerobic design require oxygen. So you can't really supply oxygen unless you have a direct way. So that's why there is this air injection. So basically same pipe will deliver air through it. So you are basically, think of wastewater treatment plants. You are purging oxygen, right? Air is the same thing. Instead of wastewater, you are putting through those waste. That's the only difference. And that means you will produce a lot of liquid, because the aerobic degradation is so fast. It's going to be, that's what happened in our body. It's aerobic because you inhale oxygen. And again, the whole goal of this one is to compress the waste as quickly possible so that you receive waste for a longer time. Then you have also combination of both. Okay, so this is a mixed reactor, as you see, aerobic and anaerobic. Some places you do aerobic, some places you do anaerobic. The top portion is the gas collection system, and the bottom portion is mostly aerobic, so that it compresses quickly. So it just depends on which one you want to do. And there is other reactors where basically the bacteria can use the waste itself to breathe. So that means this is basically for nutrients. If you have agricultural waste, it has so much nutrients like ammonia that is become toxic to many bacteria there, so they can decompose to methane and all that. So for this kind of reactor, you wanted to remove those methane, the ammonia gas. So this is just to how to collect that, create the nitrification and denitrifications. This is very rare. This is mostly for agriculture, but so that you know. All right, so these are all details you are going to learn also in the next class, next quarter, the design to some extent. You are actually going to demonstrate a project. In that class, 50% of the class is project. You work with 5 or 6 students, you come up with your concept, or I will give you some problem that you can solve as if it's a real world problem. You write a project, you discuss with each other, writing. You can design landfill, you can design anaerobic reactors for wastewater treatment plants. You can treat hypothetical locations. For instance, in Los Angeles, there are many contaminated sites. I'll give you a list of those. You can come up with a plan that could clean up that site. That's why it's very useful, because you can take those plans and talk to the people in LA County and saying that this is my class project. A lot of times also they consult with I remember one time there was a call some yard. That's where they're talking about creating a wetland, and the students, they come up with a wetland design. So it's helpful for you to actually know how you can apply this concept for the real world. So next 2 semester or next 2 quarters, I teach classes where project is your main goal. There is no final. There is midterm, so that you know how to solve the homework questions, but it's a small part of it. Right, so let's take a break. We meet at 1:12, 10 minutes from now, and then we get to air pollution. Okay, so now switching gear, air pollutions. If you think of science perspective, we have been so far dealing with water. Water moves from A to B, and with that pollution moves. It's basically fluid dynamic, and what you see in air is the same thing. Just the fluid is now become air. So that means, you are dealing with materials that can float in air. So that's the air pollutants. So what you found in water is basically what can dissolve in water. What you find in air is basically what can stay in air. Okay, so that means what can stay in air is the thing that is very small particles. So when you deal with air pollutants, those are basically fine particulates, or could be gas. Okay, so Henry constant is the most important factor of air pollution now. Okay, water solubility was the most important thermodynamical parameters for water pollutants. So everything that can evaporate, everything that can escape into air is now air pollutants. So all petroleum, if you just leave it there, it becomes, there's a gas, right? So that's why you inhale or you smell the gasoline when you are filling gas, because they are being escaped into atmosphere. So where they move, what they do, how you can prevent it. Unlike water treatments, you can do air treatment. You cannot, because there is no boundary. The moment there is a wildfire, nothing you can do. All the smoke is coming in. We have to inhale, or we just stay inside indoor. Only thing you can change is just staying inside, or basically right now we are all having masks. That's the only treatment you can do, is basically prevent that exposure by creating a filter. But inside indoor, you can create your filter. So all these rooms, air is circulated at certain rate. For COVID, there is a certain minimum rate they have to change. So what they do is they monitor carbon dioxide, because if it's not been circulated that fast, we are all emitting carbon dioxide. So carbon dioxide will build up. So what they do is they use carbon dioxide as a monitoring system to see that the air circulation is good enough or not. So HEPA filter is something that people use. So why that works, what's the reason behind it, all that stuff is basically what we are going to deal with now. So news related to air quality in LA is pretty much every year there are air quality issues LA is familiar with. Before it used to be automobile, now it's more related to wildfire, because the fire is becoming so frequent that always there is some issues. Okay, and I talk about different air pollutants, and as you see that most of the air pollutants that we cover is at the very bottom, synthetic organic chemicals. Thus concentration is very low. But how do you know which are air pollutant? Just look at the Henry constant. Okay, so basically that's concentration in air by concentration in water. It could have many different forms. It could be water to air. Let's say this is the form. If the Henry constant is higher, that means everything will be in the air, or it has more affinity to get into air. Last class, we also learned if the organic pollutant is smaller and smaller, it's more likely to be in the air. The smaller the number of carbon, they're more likely to escape into air. That's why methane has 1 carbon, ethane has 2 carbon. The smaller carbon molecules are going to be in the air. Doesn't mean that large molecules are not going to be air, but the concentration will be lower. And then organic contaminants without any hydrogen bonding form or any bond that can form hydrogen bond will prevent them to get into air, because now they are bonding to hold them each other. So if the molecules are holding each other, they are most likely going to be liquid. So that's why these are the two reasons why most of the pollutants stain on the ground: bigger carbon, a larger number of carbon in the molecules, or hydrogen bond forming functional group. Everything else, they are going to be in the air. So those are into that. But above that, everything you see over here are related to, this is natural. In Culver City, if you are living, there are some places where the radon gas is much higher. That's naturally produced. That's the natural radioactivity. And radon gas can cause cancer. So that's why it's important to know if there is enough radon gas or not. Lead is basically volatile lead, which is because of the you use lead as a coatings in for all your painting. Before it used to have lead. Now also some of the painting has lead. Gasoline has lead, but before now it is unleaded gasoline. So that means you don't have any newer gasoline doesn't have lead. But it has a legacy pollutant. It's being already accumulated. So you've been inhaling because it's fall off and then it goes up again and again. Ozones are produced naturally. Basically what happens is if you have organic chemicals, that organic chemicals can produce, in sunlight, it can produce radicals. When the sunlight is like UV light touch our skin, it produces radicals. It also produces radicals when it interact with a gas or organic contaminant. And those radicals will react with oxygen, produce ozone. Ozones are naturally produced very up in the atmosphere because that's where the atmosphere is thin. There is enough oxygen. The UV light is not blocked. So that's why ozone is produced very top. Okay. But why it is produced at the bottom is not the same reason. Because now you have this organic chemical create as a catalyst to produce ozone. So if you have this synthetic organic chemical, that also facilitate ozone productions. Those ozones are so reactive that we use for water treatment. Now imagine you are inhaling it. That ozone will damage all our lung shell because of toxic. So that's why ozone is another big things in toxicity. Particulates, that's basically dust. Every time you burn something, you produce soot, or if you have dust in atmosphere, that's basically particulate, anything with the size. And what we look for is basically less than 10 micrometers. The size. If it's less than 10 micron, we call that PM10. If it is less than 2.5 micrometer size, is called PM 2.5. The reason why it is why only these two. 10 micron, if you calculate by Stokes' law, it's not going to move further. It's going to settle very quickly. So long range atmospheric transport will not happen if it is more than 10 micron. It's just the gravity will pull them down, so it will not be a factor. So what you see on the atmosphere is basically less than 10 micron. But 10 micron will, if you imagine you are inhaling 10 micron particle, all will settle on your nose. Okay, the nose hair as well as the tube is going to filter most of them. The 2.5, that's the particles will travel into beneath our lungs and get into our lower part of the lung, which where the damage happens. Or the cancer or lung cancer, all those things will happen by the particles less than 2.5 micron. So because of that, those are separately monitored. Okay. Smaller the particle, greater into they'll get into more deeper into our lungs. Okay. Then carbon monoxide, NOx. So basically COX, NOx, SOx, sulfur dioxide. These are all things produced when you burn stuff. Okay. If you burn anything, let's say you are in winter time, a lot of times people keep the car engine on and stay inside, and if you build up carbon monoxide, it's going to basically it makes us, it's a non-poisonous gas, so you will not feel anything, you will not feel the pain, you will just go unconscious. Then you don't inhale anymore, and that's how you, I mean, that's how people die, because they don't even know they are dying. So that's why carbon monoxide is pretty bad. If you're, it's in, it's said, and also by naturally when you are exhale, you are also producing carbon dioxide, some level of carbon monoxide. So that's why in the winter time, you see all these monitoring systems in your room, fire alarm, there's also carbon monoxide alarm there. Because that's basically most dangerous things. It makes people unconscious, then they can't do any actions on that. NOx, SOx, that's basically same thing, just nitrogen or sulfur. Those are only produced when you burn stuff. Okay. So during wildfire, imagine what will happen. Wildfire, you'll have lots of carbon monoxide, lots of NOx, lots of SOx, sulfur dioxide, sulfur monoxide, all that. There are lots of particulates, not so much ozone. Radon is basically coming from ground, so it doesn't really matter. Lead is basically the every plant tissue has lead in it. So when you burn things, they'll also atmosphere get into atmosphere. So this you can see how they are coming from, and so it's very important for you to know what kind of things you should expect. So I already talked about this, why it is the case, why small particles are toxic, because they can migrate into lung. Why we talk about larger particles are remain in the air, all that stuff. Okay. In the indoor air quality, you are also looking for all these different pollutants. These pollutants are coming from mostly if you bought any materials which has paint. If you buy a plastic which has smell, smell is because of some molecule. Smell has origin with chemical molecules. So these are things you might expect. Okay. But again, these are the pollutants that are banned, so that means should not be there. So those are all treated. Then there are other things, it says what are the different pollutants, what's the source. You can see many places paints. So anytime you think of paints, because paints are designed to dry up very quickly. The way you can dry up quickly is by putting something volatile. That's the whole reason, it's air pollutant. That's why anytime you spray, if you see, go to gas car station or where they put color, they have to use the mask when they paint. Because if the paints are not dried up quickly, it's going to obviously look bad, and then obviously things will stick. So that's the reason paints are inadvertently used as air pollutants, or they cause air pollutions. Again, why you should care? This is basically says where things are deposited. And the very long, very bottom portion is where you want to protect it. That's where all the small particles will get in. These are the different diseases that can happen if you have a lot of air pollutant. Also, some people are more prone to asthma and all that. They are also related to. No idea. Last time. Hello. I didn't even know that this phone exists. Last time I was trying to call and didn't work. Okay, well. Noise pollutions. There is no class for noise pollution, but roads are designed for noise pollution. If you're living near freeway, you have to take care of this air pollution. That's why the property price are very low, or at least lower than outside within the first 200 feet of freeway, because of this, all the things that you will expose to. In whole life, you will expose to 10 times more air pollution than any other people living a little bit far. So that's another thing. If you have chronic respiratory disease like asthma, you don't want to live in the near the freeway. Just by living in LA is already a risk. I mean, long-term risk, 60, 70 years of lifetime, compared to living in, let's say, Hawaii or some other place which doesn't have that much pollutions. In fact, if you think of Delhi in India, that's the most air polluted city. 3 months out of the whole year, the contamination level or the PM 2.5 level is beyond the hazardous level by EPA. So they are inhaling as much that is totally that is putting them in a hazardous container. That much they are inhaling, which is happening right now in winter time. Okay, so that's a good way to keep it. In non-wildfire season, what contributes to bad air quality in LA? So these are different things that you can see. So now question is, what are the things that contribute to poor air quality in LA when there is no wildfire, and what's the main reason behind it? Any guess? Or let's say, what's the reason behind poor air quality in LA? Is this the climate, or is this something we do here? One example. I see that you are saying something, but I thought you were saying right thing. Can you say loudly? Yeah. Yes. Traffic. We are the problem. Okay. We are the traffic. The moment you drive the car slowly, the engine is like suffocated, like it's just staying there and it's just burning, right? Burning the oil, but it's not doing anything. So it's not converting to energy. It's converting to all this incomplete combustion, NOx, SOx, all that. So when you are not burning complete, it's carbon dioxide. It's gone very quickly. Everything in incomplete combustion will produce sulfur dioxide, nitrogen oxide, monoxide, all that stuff. So every time you are driving slowly or taking pause and break and all that, and just standing ideally, you are producing lots of air pollution. So that's why if you solve the traffic issues in LA, your air quality will be lower. But that's a different story. How do you stop traffic issues? Hopefully there is more metro. That's the reason. And if you have more metros, it's going to be helpful. So we talked about regulation last class about waste. But now these are the two regulations, 1970 Clean Air Act and 1990s Clean Air Act amendments. These are the only two that really account for air pollutions. The reason you don't see a lot of air, the regulation related to air is because you can control it. You can control the boundary. So if LA is producing, or let's say Asia is producing pollution, the air is getting into US. US is producing, that goes to Europe. So this is how you are inhaling each other's stuff, right? So it's like you can't. We have one Earth. You can do much about it. So that's why the regulation is very difficult to do, because you can't set a boundary, right? So you can't regulate internationally. What you do, it's up to you. That other country may not abide by that. So that's why it's very. In another way to say is, what US does is affecting Canada, because US is a very warm climate. So everything that goes to atmosphere is going to Canada, and because warm weather travel to cold weather. So they are inhaling stuff that we do at US. So how do you imagine Canadian government say that US stop driving car because we can't inhale all your stuff? It's not going to happen, right? So that's why you don't have this regulation different. What they in fact regulate is the source, which is basically monitoring these things: carbon monoxide, nitrogen oxide, sulfur dioxide, suspended particulate, which is PM2, PM2.5, and photochemical oxidants. They recognize these are the 5 stuff that's important to monitor. If you see there are places where the high concentrations, they want to do something about it. But it doesn't have much regulations. That's why they come up with 1990, they created numbers. They say beyond that number is toxic. They create that matrix. So there is a standard developed in 1990 for all those 6 place. So carbon monoxide, nitrogen dioxide, sulfur dioxide, PM 2.5 and PM 10, ozones and lead. So combination of that will produce air quality index. When you think of air quality index, they are only talking about those. Okay. So this is what you heard a lot of times. If you go to your cell phone or mobile phone or even Apple Watch, it says UV index. It doesn't say air quality index. Oh no, there is air quality index 47 right now. Okay. So if you see 47, right at the edge near 50. Okay, so that air quality index is all we just talk about. This is the 5 things. Okay, they mix together, give a different weight. That's factor. And in Delhi right now, it's more than 300. So you can think of, if you're traveling to Delhi that moment. In fact, there is a researcher in US, in Environmental Health Science Department. There is a conference in Delhi. So he traveled one time and he uses as a medical, because his students all travel. So they monitor the proteins that says, how much your lung is stressed before and after the travel. They see a very clear signal. Just because 5 days they spent at Delhi for a conference and they came back, all the indicators are like the stress indicators are there in the blood to show immediately that how much our body is in stress when the higher quality. So you can see people living there. It's pretty bad things right now. Okay, so these are good, bad, ugly, all that stuff you can see over here. This just tell you now what's the reason behind it and how this very qualitative aspect of it. What's the reason why these pollutants are included? Why not any other things? The reason, as you see, the 0 to 50, this is the concentrations, because it monitors the concentration. Each individual concentrations are given. Okay, because you have sensors that can monitor. If you search purple air, PURPLE, purple air, that's basically a easy things that you can install in your home, and that become a lab. So in LA, many people install there in their home just to see what's the quality. And using that purple air, you can see which location has much more. So just go to purple air, search it, Google, and you'll see the first link. You can see different locations. And you can go to your own place where you live and see the purple air, nearby any purple air monitoring system. You see the concentrations. You can see all those just to give you an idea of what are bad, all that stuff. The last thing I'll talk about is basically related to corona, how coronavirus are effective in transmitting from different locations by air, and whether stops that we do is actually helping or not. Okay, so air quality modeling is, I'm just going to briefly go through starting from what particles are important for air quality, and then we go for indoor monitoring, indoor air quality mass balance. Then next class we'll do outdoor, which is long range transport. So we'll solve the question next class. Okay, the first, this one is very easy. You did it before. How do you know that? Because now we are talking about 10 micron or less. So imagine I'm going to spray bacteria here. Like, imagine there's a spray and I spray it here. How far is it going to go before it's going to fall off? And I do the same thing for virus particles. How far it's going to go? If I do for just me talking, which is like very fine water droplet is being released. You can't see that, but if you put very dark and you put a kind of gas, you can see that. When I speak, it will be, you can see in YouTube video. Those 10 micron particles will travel certain distance. So that's how, when they did this one, they found that 6 feet is kind of good enough, not really, not safe enough. But they have to, if they say 12 feet, obviously it's very hard to implement. So that's how they come up with that 6 feet. That's a good compromise. It's not really protecting people. It has to be a lot longer than that. And second thing, you go to all these, I don't know if you have a picture now. If you go to all these restaurants, you see they create this wall, right? The plexiglass wall, so that you don't really you are protected. So that means you can take your mask and eat there, which is kind of a, it's a nice thing to do it, but it's not going to protect you because the air droplet will still migrate. It will remove majority of them just by direct, but it's dispersing. If you stay there 1 hour, it's already everything same. So they are just for perception standpoint. It's not really that much effective because if you do this calculation, you will see that they are suspended. The moment they are suspended, there is turbulent motions. So this is one this is based on the settling velocity in a Stokes law in settling that depends on acceleration due to gravity, and this is particle density. This is a density of air, and density of air is always very, very small. It's a gas, right? So density of particles is really, really, really much higher than density of air. So you can really ignore it. That difference is same as, so that means density of particles minus density of air is nearly equal to density of particles. So if you put that value, you basically, this is the equations. Velocity of any water droplets, you can calculate this, make 10 micron and see how far they'll move. You can do all the calculation, is there 6 feet enough or not, by just using these equations. This is the viscosity of air, so this is given. So let's say find the settling velocity of a spherical droplet of water of diameter 2 micron. That's what we actually, when we speak, this is the picture you see. Somebody is coughing. This is how it actually look in if you put shine light on it. And average diameter is around 2 micron, which is the size of bacteria, same way. Estimate the residence time of such particles if they are uniformly distributed in the lower 1000 meter of atmosphere, and their removal rate is determined by how fast they settle in the still air. So they're saying that within 1000 meter, that's where they're stable because they're not evaporating, all that. How long they stay? So that's the settling velocity. Settling velocity is basically G density of particles divided by 18 mu, 9.8 meter per second square. That's the acceleration due to gravity. Density of particles, these are water droplets, so that means that's the density of water, right? Yes, so that's basically 1 gram per centimeter cube. That's the water. Okay, that's the water droplet. Oh, there's a dp square. dp is at 2 micron, so 2 to the minus 6 meter square. Mu is viscosity, which is 0.0172. Gram meter second. So gram cancel. The only reason here is there is a centimeter cube, so that you have to change that to 1 meter is 100 centimeter. So 100 centimeter cube is same as 1 meter cube. So 100 times the cube. That way all things cancel out. 100 times 3, 100 to the power 3. So this 10 to the 6. So another way to write is, this is centimeter cube is same as 1 meter cube. So if we put all these, 1 second cancel, all those things are there, is just answer will be meter per second. And then you can calculate for one, let's say average height of a human, let's say 6 feet, let's say 6 feet or 5 feet, or let's say 6 feet for easy, 2 meter. So you see how long it will take before that 2 meter will settle. It takes a long time. So you can't really protect them unless you use mask. Calculate that, okay? So, and then you can calculate time is basically distance by velocity. Distance, let's say 2 meters by velocity. 2 meters is the height of average, let's say the tallest human, not tallest, let's say that's the one you want to settle as quickly as possible. Or think of the height of the room. Height of room is roughly 3 height, so that's 3 meters, 15 feet. Then you can calculate how long before it settles. It will be a long time. Okay. And if there is an initial velocity, it will go exceed that 6 feet distance. So what it does is that barrier you see, if somebody is coughing, that basically will remove that cough. It doesn't migrate further. So it's fall down there or stick there. That's the reason they keep it. But if a lot of people are coughing, talking for a long time, they're everything more, they'll just disperse. Entire room will fill up with that. That's why it's more effective to eat outside, because then the atmosphere is going to be the whole thing. You can't get diluted very easily. Inside indoor is very difficult, unless you have a filtration system that's going around quickly. So indoor air quality, I am not going to cover now. This is just a mass balance that we'll cover next class. So next class, what we're going to do is indoor air quality and outdoor. So we'll solve indoor air quality issues as well as outdoor in the following class. Any question about homework or stuff that you are concerned about? I'm going to stop recording.